Second module in the fire science probabilistic risk assessment course. And so we're going to be discussing some of the issues in fire science related to nuclear power plants, but more specifically, just the details of fire science that will allow you to analyze what issues occur in nuclear power plant risk assessment and safety issues. As you look at the corresponding text here, so this is from the calendar, and it tells us that in this lecture 2, we're going to be looking at combustion thermochemistry, which we began last lecture, chemical balances, stoichiometry, the first law. We'll discuss the adiabatic flame temperature, the heat of combustion, and something that's very important in the analysis of fuels, which is the heat release rate of a particular fuel packet. So to get started, I'd like to actually show a little film demonstration of some of the issues that we've been talking about in terms of the life of a fire. So we talked about the evolution of a fire in the so technical difficulties, of course. We talked about the evolution of a fire in the last class, in the last lecture, and I want to show a little video clip from a National Institute of Standards and Technology video sort of training guide on how quickly a fire might evolve within a compartment. So last time we talked about what would happen if a fire might be started on a sofa. So this time let's look at a relatively well-known in the fire science area video that talks about the time it takes for a fire to engulf a room where a Scotch pine tree has been ignited. So before starting, I want you to all come to some determination for yourself. What does it mean for a room such as this living room to become untenable from the perspective of fire? 2, how long do you think it's going to take if a small ignition source, and so the ignition source is a small lighter that's placed at the bottom of this tree, how long is it going to take before this room becomes untenable? And finally, we've talked about flashover, for example, in this last lecture. How might you identify flashover for a compartment like this? Okay, so first of all, you're thinking about how long might it take before this is untenable. Let's go through this video and try to understand that. So as this tree is ignited, you see that a dry tree quickly ignites, and then you see the products of combustion quickly lift up and envelop the ceiling area of this structure. So on the order of 19 seconds, we see that there's this dark, hot upper layer. So this is typically called the upper layer in compartment fire analysis, that has now caused ignition and flame spread to adjacent fuel packets. So this sofa over here is on fire. This chair here is on fire. And so let's continue. So I hope that this is clear. I'm going to stop it here again. There's a vapor, there's a white vapor cloud that's coming off of the carpeting here. Remember, we talked about the fact that there's a pyrolysis process that occurs in which the bonds within these polymeric materials are broken because of, again, thermal insult, and that causes the liberation of these relatively small or lower molecular weight hydrocarbons, which is, again, the fuel. So we continue. We see that this upper layer is descending. We see ignition, again, of secondary fuel packets. This stuffed animal was placed within the compartment to highlight this idea of flashover. So this stuffed animal is remote in some sense from all these other fuel packets, but the intense thermal radiation from the hot upper layer, which can reach temperatures of hundreds of degrees Celsius. So we can get 600, 700, even sort of, in some cases, locally 1,000 degrees Celsius in this upper layer. We'll talk about how those temperatures compare to adiabatic flame temperatures shortly. But the intense radiation, thermal radiation from that, has caused, again, pyrolysis gases to be liberated from this stuffed animal. And shortly you'll see that this itself will ignite. And so we get ignition everywhere. And this ignition throughout the compartment is, again, called flashover. So this flashover event occurred on a very short time scales. And again, we saw really a transformation from this this confined fire on the tree to a fire that was spread throughout the compartment. And now I'd like to just show one other video, which is closer to what we talked about last time. And so in this case, remember we said that if this is a sofa that's on fire, that we should observe a few distinct stages in it. So initially, we had this ignition process. So we didn't start with the smoldering process like we talked about from a cigarette. This is actually an ignition, a direct ignition process where a hot ignition element causes an immediate flaming reaction. And so this flaming process initially is localized, and from the perspective of the flame is absolutely, this little fire, this really diffusion flame is unaware of the environment. It's unaware of the fact that it's in a room of this size. The room could be larger. It's essentially an open air flame, an unconfined flame in any sense. Now, we talked about the fact that there's a flame spread process that occurs. So in that flame spread process, the heat transfer from the fire is causing adjacent fuel elements on the same sofa to release their pyrolysis gases, and in doing so, this causes this diffusion flame outside of the sofa to continue to grow. So we talked about this, again, as being a flame spread process. So we see this flame spread process taking place, and as we talked about before, upward flame spread, because of buoyant effects, is faster than lateral flame spread, and it's going to be shown to be faster than downward flame spread. Now, the color of the flame, so in this case, you see, I guess it's not particularly clear, but it is this yellow orangish color. That color is because of the carbonaceous, these soot particles that are formed by cooking the fuel vapor. So the fuel vapor is a CH, it's some C subscript with some subscript times, H with some subscript. So some carbon hydrogen system, a hydrocarbon, and as you heat it up, you liberate the hydrogen. So you're getting rid of the hydrogens in some complex dynamic. There are lots of different mechanisms that have been proposed for how soot is formed, and you're left with these carbonaceous materials, this soot material, and the soot, being a solid, is a broadband radiative emitter as compared to these gases. So gases have line properties in terms of their radiative properties, but the soot, once you have really beyond about 1 part per million of soot within a combustion product gas, that becomes the primary radiator, and that radiates in a broadband sense, and that's what we're seeing in terms of this yellow color. So we get this intense soot radiation, and we start to see some smoke coming out of this flame. So the soot particles that are formed within it actually pop out. They're not oxidized, and they continue to evolve and grow actually as they go up. Now, if there had been a smoke detector here, we imagine that smoke detector would have alarmed probably around now, because on the order of 100 kilowatt fire for a room of this size would likely ignite, will cause enough particles to be lofted to start a smoke detector. 100 kilowatt fires like the fire that you might have in a waste paper basket. So now, again, we've seen more vertical flame spread than we've seen horizontal flame spread. We've talked about this again. It's because of this wind-aided flame spread process. Soon we're going to see secondary ignition packets that are going to be ignited. We see that we haven't caused that layering of significant layering in the ceiling associated with the hot products, but we're starting to see that evolution. So there's this continuous sealing jet production and evolution, and now we're seeing the darkening of the upper layer because of all the products of combustion that have, because of stratification, that have been lofted upwards. Okay, so again, growth of this fire because of the flame spread process. Now all of a sudden, we have this upper layer has grown, it's hot, and the radiation from that upper layer is actually helping in terms of these lateral flame spread processes. Heat transfer is the mechanism by which condensed phase fuel packets become vaporized, essentially. And so the liberation of the volatiles within these condensed phase materials is significantly augmented by this upper layer. Now, something else I want you to note is the stratification that occurs in this system. We have a dark, hot upper layer and a significantly cooler, clearer lower layer. So one of the things that kids are taught immediately in school when we talk about fire drills is stop, drop, roll. And so the stopping and the dropping is to make sure that you're able to access the remaining oxygen in the lower layer and are not breathing in this hot, toxic upper layer gas. Okay, so the drapes have been involved. The lower layer continues to descend. It looks almost like a water-oil mixture. Again, it's a density gradient, a density difference that's causing this. And you see, again, sort of distinct layering between the top and the bottom. At about a temperature, an upper layer mixed temperature of about 600 degrees Celsius, this is, again, so optically thick that it's radiating like a black body. At about 600 C, we get sufficient radiative intensity. Again, this is all thermal radiation we're talking about, to these lower layer fuel packets, that we actually get heat fluxes on the order of 10 kilowatt per meter squared. And remember that the solar incident radiation is about a kilowatt per meter squared. So we're talking about very intense radiative fluxes. Those radiative fluxes are what are, you see, okay, so I want to show you this again. You see how, I'm going to maybe try to go back just a little bit. So what we saw here is this sofa, because of the intensity, splits open because, again, of the heat that is causing damage to it. And so just right around here, we get that splitting. More volatiles are, of course, released. And we see that we're moving towards this flashover event, where we talked about the flashover event as being indicative of a absolutely untenable condition. So based upon even these heat fluxes, it's very hard to imagine anybody can survive these intense fluxes. But once we go to flashover, where you see, again, the carpet curling, etc., really, this has become beyond untenable. Okay, so at this point, you have a much better understanding of the different issues that we see in these systems. And of course, my tablet goes off, so let's switch back to the desktop for a second and start getting this going. So we talked about the different types of fuel packets that you would see. We are now going to talk about how to analyze these combustion gases or these combustion systems to get a better sense of what these fuel packets really look like and what we need to deal with in terms of analyzing them. Okay, so we're interested in talking about combustion thermochemistry. we recognize that in simple, clean combustion experiments, the fuels are very well characterized. In fire, the fuels are very complicated, and in fact, we don't really know what the elemental composition generally is. So in simple combustion science applications, the fuel is well characterized. We'll say usually. And again, this is in contrast to fire applications. And so sometimes, you might talk about fire's wild or feral combustion. So, combustion is, or at least, you think about it as some sort of controlled combustion process. Now, combustion really is sort of the overarching science that also encompasses fire. But fire, in some sense, is a technology. It's an industry. It's again this wild. It can be this wild combustion process that we're trying to manage and deal with. So in fire, the fuels are much more complex, and there's an aspect of it that, in many cases, the fuels are engineered. So when somebody puts together a particular blend of polymers for some mechanical property, the comfort, for a foam, or insulating property for something that goes over copper wire, there are all sorts of different additives that are put in there to achieve some engineering function. And oftentimes, the impact on fire safety is either not dealt with or dealt with by adding other chemicals, and so you get this complex soup of chemicals in there to deal with the issues of fire. Now, what we'll do is we'll talk about what is done with simple fuels first, and then we'll make the case that for fire that other types of things have to be done. So I'm going to sort of do a more multimedia type issues in terms of dealing with this. So maybe to put some context to this, when we talk about this combustion thermochemistry, let me identify where we want to go and what we want to look for at the end of this module. So from the perspective of the goal of this module, really, is for the student to understand what the heat release rate is, and have some sense of how to calculate it. Okay, so this heat release rate, which we're going to refer to as HRR, and we'll also refer to it sometimes as Q dot, has units of watts, but it could be typically kilowatts or megawatts. So what this is it's a measure of the exothermic power of a fire. It's a measure of the overall amount of heat that's released by something burning. And so, here's a little bit of philosophy, really, in terms of this discussion. The reasons that we design or analyze for fire is we're looking at ways to either come up with mitigation strategies, looking to make sure that our designs, structural or otherwise, are effective in containing the fire, or sometimes in reconstruction we ask the question, what type of fire caused this amount of damage to occur? And we use a whole range of different types of analysis models, from computational fluid dynamics to simple hand calculations. Now, in fire modeling, we are often less interested in, and this is going to sound odd, but in the details of the flame, but in the details of how the flame and the fire products will affect safety. And that could be life safety, or it could be property protection, etc. So let's just point that out. So in fire modeling, and fire modeling really encompasses whether it's design, so it could be we're trying to do system design or some sort of reconstruction. So we can use modeling to do either one of these things. So we focus on the impact of the fire. So we focus oftentimes on the impact of the burning process, and we use a model, a simplified model for the thing that's burning. So one of the things you're probably thinking to yourself is, well, why are we going to go through some of the details of understanding flames and these more detailed pieces of this? I think it's really for context. We want to understand how these things fit together. So we use a simplified representation of the burning process. I'm going to put burning physics / process. And I want to just maybe, again, just make it clear why that's important. If we're talking about whether it's a Christmas tree fire or otherwise that we were looking at in those videos, and you think about the scale of the room. So the room is on the scale of a meter, a few meters. So it's a maybe 3 or 4 meter room. So order meter sort of length scales for this room. And what we'll see is that we talked about the fact that a flame can be considered an interface. It's not. There's all sorts of interesting detail. People spend their research lives describing the structure and the properties of this flame. So the length scales, though, associated with a flame, really, as an interface, but sort of blown up, are on the order of 100 micrometer. So 0.1 millimeter. So you see that we're talking about a 10 to the 4 length scale ratio between any particular size of a room and the size of this flame. So the flame, which is this fundamental component, is 10 to the 4 times smaller than the characteristic dimension of a room. And to resolve the flame, you need much finer resolution than that 10 to the 4. I mean, you'd have to do, 10 to the, you'd really have to resolve on the order of at least, 10 10 micrometer, maybe even some places a few micrometer to just understand what's really going on in that flame. Then the characteristic dimension or the characteristic length of the room. So, well, 10 to the 4, that's not prohibitive, but it's prohibitive when you think about computationally looking at 10 to the 4th cubed. So if you are going to resolve something that's three-dimensional and you have to resolve 10 to the 4th times on each dimension, you're talking about 10 to the 12th type volumes to be able to resolve that. So to resolve this meter cube volume at 10 to the minus 4 meter resolution, requires 10 to the 12 volume elements. Well, that's not happening, okay? So this requires modeling. So this suggests that we don't model the flame or don't resolve the flame, but we model the impact or the effect of it. Okay. So, practically, I'm going to go back to the sofa on fire. So practically, for the sofa on fire, what I'm telling you is that it's really hard to model the evolution of the pyrolysis gases, although, the simulations are getting more sophisticated and we're able to do more, and that it's really hard to model the burning process above it. But what can we do? Because we want to know where these products are lofted, what's the heat transfer to other fuel packets to see whether or not they ignite. And so this is a part where measurement science actually comes into play. And so from a measurement science perspective, and so I'm just going to, I'm going to go forward and come back. I'm going to cheat a little. So from a measurement science perspective, I'm going to switch to the desktop. There are lots of research facilities throughout the country and throughout the world that try to make careful measurements of the amount of heat that's released when things like a love seat is ignited. And so what they'll do is they'll ignite this love seat in a careful experiment, and they'll measure this heat release rate. So this is heat release rate in kilowatts versus time in seconds. And so the integrated amount of heat release rate over time is some energy liberation in this burning process, but we see that there are instantaneous values for what this heat release rate actually is. And we see that the peak heat release rate, and this is staggering, for a love seat burning is 3 megawatts. So think about that, 3 megawatt heat release rate for a love seat burning. And so you have in your living room something that can generate that amount of power. That's incredible, actually. I dropped my microphone, excuse me. My enthusiasm caused me to knock off my microphone. Okay, so a bunk bed. So a bunk bed, all of a sudden now we're talking about 4.5 megawatts for a bunk bed on fire. So you think about this. To be able to design mitigation strategies against things like this, you again have to understand what kinds of values you should get. There's an enormous variation, so it should be statistical because these are not, again, delta function sort of inputs. A mattress, again, 700 kilowatts. So in these real scale applications, the key is to use these large-scale calorimeters. And there are large-scale calorimeters, like I said, all around the world. And we'll talk about the details of how these calorimeters function. So to put this, again, into context, this is what we're trying to understand heat release rate, because heat release rate is a critical input into fire models. It tells us how much power is being liberated in a burning process. And it circumvents knowing all the details of the burning process for an individual fuel packet. Okay, so I'm going to talk to you about how these large-scale calorimeters work. In fact, it might be useful to think about it from a historical context. So historically, when people wanted to understand how much power was liberated by something burning, and we haven't gotten to all the details yet, but you'll see this. They said, okay, well, look, let's collect the fire gases under something burning. So if I want to know how a particular piece of plastic or a particular piece of foam burns, sort of the simple way to do it is I'd stick it on a load cell. So I measure the mass as a function of time after I ignite it. So I ignite it, I got a flame, I measure the mass loss rate as a function of time, I measure perhaps the temperature in the stack, and I measure the volumetric flow rate. So this V dot, we'll call the volumetric flow rate of the gases. And I measure mass, like I said. And so I do a simple energy balance on this system. And we haven't talked about energy balances in detail yet. But I do a first law of thermodynamics energy balance on the system. And in words, I say, well, the amount of energy that's liberated that amount of energy per unit time is going to be responsible for my increase in temperature of these product gases. So the temperature rise of the product gases that I'm measuring in that stack. But that's not the only place the energy goes, is it? Because I get radiation, so I lose thermal radiation like that. There's conduction maybe into this, so I've got parasitic thermal losses. And those parasitic thermal losses, I'd have to be really careful. Even this gas, I'd have to insulate the heck out of this, this collection system so that I don't have conduction and then later convection off of here. So I've got all these losses that I have to account for, and it's never really very well done. And the reason I have the load cell is because I believe that there's some, this is again sort of historical, that there's some intrinsic energy density to this material so that I should be able to integrate the amount of energy that I have sort of consumed in the burning process, and this should be comparable to what sort of this integrated amount of power that would have been liberated with respect to time. So this is sort of the first approach. And like I said, there were all sorts of problems associated with that. And we'll go into more detail on that soon. In the mid to late 70s, perhaps even early 80s, there was a realization that this amount of energy that was liberated, or that this energy content called the heat of combustion, I'm going to write it down. So let's put this in perspective. So there's an energy density associated with burning any material. And so this says that for a kilogram of some material burning, there's n kilojoules liberated. Okay. This quantity is called the heat of combustion. So the units of this are joules per gram or kilojoules per kilogram. Okay. So this is the amount of energy liberated for when this material is burned. And it varies all over the place. So, you know, different materials have different heats of combustion. So we have things like 44 kilojoules per gram for something like propane or methane. We have 18, 20 for, say, polyurethane. So it varies all over the place. If I know how the mass of a material is changing with respect to time, so if I know that the burning process because of a load cell, so say a load cell records, that's a different way of spelling records, reords. So say a load cell records a change in mass with respect to time of some burning material, some burning process. So this is called mass burning rate. Then, if I know the delta Hc, the heat of combustion of that material, then I know what the heat release rate is as that material burns. Why? Because this HRR that we talked about, this heat release rate, is equal to the mass burning rate times this delta Hc, this heat of combustion. Let's make sure the units make sense. So we have kilograms per second times kilojoule per kilogram. So we have this burning rate, kilojoule per second, which is, again, kilowatts. Okay, so that's great. But like I said, you don't know what that delta Hc is. But there was a realization that the delta Hc on an oxygen basis is pretty much constant. So even though it varies like crazy as you vary the fuel that is on a fuel basis, it's not on an oxygen basis. And let me show you that in a second. So I'm going to quote you the number, and then we're going to go back and show what it means. So delta Hc on an oxygen basis is about 13. We can either talk about it as kilojoules per gram O2, or 13 megajoule per kg O2. Okay. Now, I'm going to get your attention here, because so what all of a sudden happened is, if this is true, and then I burn a material, I know, and we'll talk about I'm starting to use things. I know the oxygen concentration in the ambient. So I pull in this oxygen, I measure volumetric flow rate, and I measure the amount of oxygen in the flue gas in this product stream. And I ask myself, I say, hey, how much oxygen was consumed between the ambient and this product stream? And if I consumed a certain amount of oxygen, that is related to how much heat was released based upon this delta HC. Okay, so there's a lot that needs to be filled in, but this is the basis of something called oxygen consumption calorimetry. So it changed in a significant way our ability to determine heat release rates and to quantify them much better than we had done before. So it's really not a calorimeter per se, but it has the effect of calorimetry. Okay, so I'm going to quickly jump to the PC, and I'm also going to check the time. And so this is our basic O2 consumption calorimeter. There's a mass flow rate of fuel. There's a mass flow rate of oxygen. There's this hood that captures the products. There's exhaust gas and a sampling system. And there should be a dot over the Q here, Q dot, which is per unit time. This heat release rate is about this 13 times the change in mass flow. This is an m dot of O2. Okay, so this is an important piece of the puzzle that we're dealing with in these types of problems. Okay, now I want to just there's an ASTM standard associated with it, ASTM E1354. This is a small scale test where we're again putting something called a cone heater. This is sometimes called a cone calorimeter. It's called a cone calorimeter because there's a heater here that has a radiative flux to the sample, and again, measuring the product gas stream tells what the heat release rate is. At the same time, there's actually a load cell that measures the mass loss rate, and so from that, one can infer what this heat of combustion is for these samples. Okay, so we've talked about that practically the heat release rate is an important quantity for characterizing fire systems from a measurement perspective, and we've talked about the fact that it's something that's experimentally determined. Now, I want to quickly talk about how to, alternate ways of getting this heat of combustion. Okay, so to start, I know this is a little bit, we're going back and forth between the laptop and the PowerPoint, but last time we said that a simple way of characterizing combustion systems is reactants going to products. So reactants to products. But if we add a little bit more detail, we can say it's a fuel and an oxidizer going to products. And so the details obviously matter in terms of what the fuel is. The oxidizer for most of our applications is O2. So really what we're saying is for a very simple problem where it's a hydrogen gas, hydrogen plus 1/2 O2 goes to H2O. So this is a balanced chemical reaction that talks about this particular process. Okay, and we'll talk about what a stoichiometric reaction is. And the stoichiometric reaction is when we don't have excess fuel or excess oxygen on the product side. So the product side is the right-hand side. The reactant side for these problems that we're going to talk about is the left-hand side. Now, there's a term that we'll use, and these PowerPoints will all be posted on the site. It's the stoichiometric coefficients, and these are the relative amounts of oxidizer and products for a stoichiometric reaction. So here, in this case that we've talked about, we have 1 mole of hydrogen, 1/2 mole of O2, 1 mole of water vapor. And so the stoichiometric coefficients are 1, 1/2, and 1. Okay? And we can also talk about this system in terms of mass, because there's a mass conservation process that has to occur here. So we have 2 grams of hydrogen. We have 16, so 1/2 of this 32 is 16, so we have 16 grams of oxygen. So the 2 grams of hydrogen, 16 grams of oxygen give us this 18 grams of H2O. As we noted, though, hydrogen is great, and actually hydrogen is an important fuel risk in power plant applications. But again, as we talk about fuels, there are a variety of fuels in actual fire applications, everything from simple hydrocarbons like methane, propane, etc., to more complex mixtures, gasoline, kerosene, to solids, coal, wood, paper. So in developing all of this, though, we need to understand some basic issues in terms of stoichiometry and the characterization of these gas systems. We model air as 21% oxygen, 79% nitrogen. So we understand there are other things in air, but for the purposes of combustion or fire, this is adequate in terms of modeling the impact of air on the combustion evolution. And we'll talk quickly about the different types of ratios one uses to describe combustion systems, the fuel-air ratio and the air-fuel ratio. Okay, I'm going to skip this slide. Well, no. Okay, so in this slide, what I'm saying here is that if you have methane plus air, and so we say that air is oxygen and nitrogen, there are a few ways that we can represent that. We can talk about the fact that there are, so remember, the stoichiometric coefficient is an indication of the number of moles that are present. So when we have air as O2 plus 3.76 N2, there are 4.76 moles of air. Compositionally, the 3.76 divided by 4.76 is 79%, and 1 over the 4.76 is 21%. So this model of air is clear here. Now, for this stoichiometric reaction we're talking about, we produce carbon dioxide, water vapor. The nitrogen is a diluent. It doesn't participate, and it just sits back over here as it was part of the reaction stream. It's part of the product stream. And you see the 2 times 3.76 is the 7.52 N2 that we have here. Okay, so this is a balanced chemical reaction. When we talk about the stoichiometric, because again, it's balanced and there is no excess fuel or excess oxygen. So we talk about that as a stoichiometric condition. We can talk about the fuel-air ratio under stoichiometric conditions as the mass of fuel divided by the mass of air. So the mass of fuel is our 16 grams, our 12 plus 4, 12 carbon, 4 hydrogen, 16 divided by 232 plus, again, 7.52, 28 nitrogen, molecular oxygen. And so we get a fuel-air stoichiometric ratio of 0.058. When we talk about the equivalence ratio, this is the ratio of fuel to oxidizer compared to the stoichiometric condition. So when you hear that the equivalence ratio is less than 1, we understand that that is a fuel lean condition. When it's greater than 1, it's a fuel rich condition. When it's equal to 1, that's stoichiometric. So it's, again, simply the fuel-air ratio divided by the fuel-air stoichiometric ratio. And so, again, for this simple example of methane combustion, the air-fuel ratio, the over bar means on a mole basis. On a mole basis is 9.52. The air-fuel ratio on a mass basis is 17.19. Fuel-air ratios, which are more common in combustion, mole basis 0.105, mass basis 0.058. And again, these slides will be available so you can work through this example. Okay, last thing we're going to talk about is flame temperatures. So I said before when we were talking about when a fire is consuming products or consuming fuel in a compartment, that if you get 1,000 Celsius temperatures in the upper layer, that's really hot. But then here I'm showing flame temperatures for a range of hydrocarbon fuels, except for hydrogen, which is just hydrogen, where the flame temperatures are significantly lower than what we talked about. And so in these cases, flame temperatures, and these are actually more not computational. These are experimentally sort of provided flame temperatures. But you see it's all about 2,000 C, okay? So what's the discrepancy? Why are these significantly hotter than what we're finding in the upper layer? Well, okay, if the flame is an interface, so this is the flame, and in these cases the flame is a turbulent flame. It's moving like this. It's being distorted. If you're making your measurement of temperature at any location, what are you really measuring? You're measuring all sorts of different things around the flame temperature, and you're not necessarily measuring the flame temperature. So in a well-controlled laboratory experiment where you might, for example, have either a laminar flame where the flame is just sitting there as an interface, and you can put a thermocouple or some other device very close to it or probe it, then you can really identify the flame temperature. Otherwise, you're measuring some average temperature. You've got soot, radiation. You've got all sorts of other losses. Okay. The way that we determine the flame temperature for these simple combustion systems is by using a thermodynamic property called the enthalpy. And so we rely on the first law of thermodynamics, and the first law of thermodynamics can be simplified for problems like this to essentially say that the change in enthalpy is equal to the amount of heat that's been liberated in the system. Now, what I've shown here is the enthalpy function for reactants and the enthalpy function for products. And the heat of combustion can be thought of as the energy difference. This enthalpy is an energy difference between the reactants and the products. So at any given temperature, the reactants are higher energy than the products. Now, if we're in a constant enthalpy process, that is, we're converting reactants to products, then what we're really doing is we're seeing that there's a temperature change that has to be associated with that. That temperature change, when you add that temperature change to the initial temperature or the reference temperature, in this case is 25 C, that final temperature that you get can be thought of as that adiabatic flame temperature. And the adiabatic, of course, refers to the fact that there are no heat losses that are occurring. This example is going to be available where, again, we have methane combustion. We can calculate the heat of combustion in terms of the enthalpies of formation, or we can find them by lookup tables. And we find out the amount of energy that's released in this transfer process for this particular reaction system. Okay. This really concludes our discussion on combustion thermochemistry. I will post these lectures online and also review some aspects of these in Lecture 3. All right, I will see you shortly.